Good afternoon, everybody. Welcome to my presentation on protein modeling with the Wolfram Language. I'm Bob Nachbar. I am a senior project director in Wolfram Solutions, and I also work with the chemistry and biology teams within the company on Wolfram Language for those areas. So we've introduced proteins and biomolecules to the language a couple of versions ago, and mostly we just had the experimental geometries available from sources like AlphaFold for folded structures, or ESMFold, or the Protein Data Bank PDB for experimental structures. And that's great. It's a good source of data to study structure and things like that. But protein chemists often want to do more than just that. And when I was in the pharmaceutical industry, we often used enzymes, structures of enzymes, to try to design drugs to fit into them. And, working with protein structures in a modeling environment is different than just viewing them or computing properties, distances and things like that from crystallographic structures. And so I've been working on some extensions to our capabilities through a Packlet to provide modeling capabilities of protein structures. So I'll skip the abstract because you've all read it. So, the first question is, aren't proteins and nucleic acids just big molecules? And the answer is yes and no. They're both made up of atoms and bonds, like small organic molecules and inorganic molecules, but they're different because they are, number one, polymeric. They have a very limited range of monomer components that are used to make them. For proteins, it's just the 20, generally the 20 canonical or proteinogenic amino acids. And for DNA and RNA, there are 5 different bases. 4 of them used in DNA and 4 in RNA, but there's 1 in RNA that's different from DNA. So, we have that. And another thing that is a feature of them, because the repertoire of monomers is so limited, they have a predefined set of labels that are used on all the atoms within the monomers. And so protein chemists frequently talk about, C alpha, C delta, H beta 1 and things like that, referring to very specific atoms in the structure. And so I wanted to be able to enable that capability as well. In Wolfram Language, molecules don't have labels. They just have an index in the list from the atom list property that you can get from a molecule to know if you want to reference a particular one, for example, to measure a distance between atom 13 and atom 28 or something like that. And somebody else who made the same structure, but the atoms are in a different order, would have to use 2 different numbers. With proteins and DNA, it's a very consistent set of atom labels that are used. And so I want us to be able to make use of that so that it's easier for protein chemists to do the work. Okay, there are 3 main sources of 3-dimensional protein structures. I had mentioned the Protein Data Bank here, PDB, largely experimental, X-ray neutron diffraction, NMR, cryo, EM as well. There are some theoretical structures in there, not very many. AlphaFold is got all theoretical structures. These are structures from protein folding. The deep learning neural networks are used for that, as well as for ESMFold. And we do have a service connection to ESMFold. And the biomolecule function itself, if given a sequence, a biosequence, or a string that represents an amino acid sequence, we'll go out and use that service to fold the structure and return a folded structure for you. All of these different sources of structures, though, the structures you get from them, they're not created equal. Oftentimes, hydrogens are not observed by experimental methods, either completely that there are no hydrogens in the deposited structure in the database at all, or sometimes partially. It might have, 98% of the hydrogens, but there were a few that were just exchanging with water molecules too frequently to be observed well, to get a good diffraction reading, and so they weren't determined. Or other types of disorder will cause that problem. Sometimes there are short stretches of residues that are not observed, again, for disorder, things like loops between helices. Even within a crystal, there's room for motion there. And if they are wiggling a bit on the experimental time scale, the diffraction patterns from them are blurred and not measured well, and therefore their positions are not determined. And then occasionally there will be individual heavy atoms, carbon, nitrogen, oxygen, etc., that are not observed, again, due to disorder. And the theoretical methods, the neural net folding methods, both AlphaFold and ESMFold, omit all hydrogens. They only return the heavy atoms for the structure. So this really means that there's a need to do editing of biomolecules once we get one into Wolfram language, so that we can be able to compute binding energies, for example, do molecular dynamics, calculate active properties, things like surface areas and volumes, and so on, that the language can do so easily. You want a structure that is, that is valid, that is a real representation of the biomolecule, not just what it was happened to be observed experimentally. So this was the reason why we need to be able to modify a biomolecule once we get it in. And there's even more. Besides just making the structure complete, biologists often want to study the effect of changing the structure, changing the amino acid sequence, and what is the effect on the structure? What is the effect on the dynamics of the motions of the helices or the sheets, for example? Does it induce just a small change, or does the fold of the protein change drastically? And then they also want to see what happens in molecular dynamics simulations of the same sort of changes. And so what they want to do is essentially, for example, take the phenylalanine here on the left and convert it to a tryptophan on the right, without disturbing the rest of the structure. So they want to do what's often called a point mutation. One could take the sequence and make the substitution and refold it, but there's no guarantee you're going to get something close back. It could be very, very different. So it's, doing that with the sequence is a very different computational experiment than just replacing the phenylalanine with a tryptophan. And this is a very common task in protein design and analysis. And in fact, this was a user request that we had last summer that started all of this work on supporting protein modeling within the language. And so the talk that I'm going to give this afternoon is based on the workflow for doing specifically this particular type of point mutation, and a few other things that we did along the way that have proven to be useful. So I'll describe those as well. Okay, so where do we begin? Thinking about the problem, the internal data structure for a biomolecule is very different than it is for a molecule. And so I had to, think about things differently. It is a hierarchical structure. At the top level, there are models. Some structures have, you might have more than one model. NMR-determined structures often have many models because they're solving an ensemble of that, and because there is a great deal of variability in the results that you get based on the NMR data. Crystallographically, you might have a model where a loop is folded one way in one model and slightly differently in another model, both derived from the same diffraction data. Underneath models, you've got all the different chains of the proteins or the amino acids. And then within each of those chains, you've got lists of residues. And within each of the residues, you've got lists of atoms. So it's very different than a molecule. And because it is hierarchical like that, good approach was to treat the protein as a set of interchangeable parts at the residue level, because that was the type of change we wanted to make. We didn't want to go in and change a single atom the way you typically would do with a molecule. We wanted to change a whole residue. So that was the approach I took. And to do that, we want to be able to do is extract residues as molecule objects, because we can do lots of work with a molecule object. And then we want to be able to take that molecule object and put it back into the biomolecule to replace, a residue that's already there once we've modified it, or taken another residue, taken that tryptophan and matched its geometry as much as we could to the phenylalanine before we stuck it back in. So those are the sorts of things that we wanted to be able to do. So we need to be able to extract and replace. And in between, what we want to do also is to conform the shape of the new residue so that when it gets, when it goes into the biomolecule and replaces the one that's there, it causes minimal interference from especially nearby side chains. So we built a tool to do that as well. And then, as I had already mentioned, a lot of structures are missing hydrogen atoms, either all of them or some of them. And we want to be able to restore those to the structure so that we can do appropriate calculations of things like surface area and volume, and energetics and things like that. And what's tricky about the replacement of hydrogens is that proteins are ionizable. They have side chains with acidic groups and basic groups. And depending on the pH, the different groups, they have more hydrogen atoms than usual or fewer. At physiologic pH, which is 7.4, most acidic groups, aspartic acids and glutamic acids, are ionized, and they have carboxyl groups with negative charges on them. And all of the basic groups, side chains, arginines, lysines, histidines, those are protonated. They have an additional hydrogen on them with a plus charge. So as the pH changes, we have a different configuration of hydrogen atoms on the protein molecules, and we want to be able to add the hydrogen atoms appropriately for the given pH at which somebody wants to study the protein molecule. Okay, so to do all of this, I made a new packlet called Protein Editing. It's available here at this link. You can download it and install it. It is still in its initial development, so it's version 0.4.1 right now. It has not been submitted to the packlet repository because there's still a number of things we'd like to do, and not everything has been thoroughly tested. And I'm sure there are many cases where some things will break. There's a great variety of structures out there, and we haven't tried them all in the system to know, how robust it is. We've, discovered a number of bugs. We've been able to take care of them, but there are probably more out there just waiting to say gotcha. Okay, so where do we begin? As I'd said, we wanted to think about working with the proteins as, at the residue level, and we'll need a collection of building blocks for them. And these would be the 20 canonical amino acids. And there is a data set of them at this link here for the PDB Protonation Variants Companion Dictionary for the 20 amino acids. And they cover a number of different backbone linkage forms: N-terminal, C-terminal, free amino acids, and Squitter ions. Here are the examples for alanine. This one here is the C-terminal one with the carboxyl ionized, and this is the C-terminal with a carboxyl with a proton on it. This one is the free amino acid. So we got a proton on the carboxyl and just two on the amine. This one is the Squitter ion form of that, where the hydrogen on the carboxyl has moved to the nitrogen. So overall, it's still neutral, but it is ionized internally. We've got an N-terminal form here. This would be the form that we would use for the first residue in the chain. where the amine is protonated. And this one here is the linking version. And all the ones that are involved in chain building, the C terminal, the N terminal, and the linking ones, the connections to the adjacent residues, the amine on the one end and the carbonyl carbon on the other, have a negative charge because this is where the bond was broken, was cut. And this is where they would be rejoined when you splice a new one into a chain, or when you extract one out, you take it out like this. This is the way they built that database, and we've just followed suit. On top of that, there's a lot of side chain variability as well. These are the different side chain variations for histidine. At more physiologic pH, the imidazole group has an extra hydrogen on it here. And in some cases, it could be missing. This is a neutral one here. And so we've got them with a third descriptor here for the side chain protonation state. And so the data set has all of those. And we can access them through a function that you have described on the next slide, which is standard protein residue. So to get started, let's load the Packlet. And the standard protein residue, in the simplest form, it takes just the three-letter abbreviation for the residue, and will return a molecule object corresponding to that. You can also provide the backbone and the side chain states as well, depending on your modeling needs. It's also convenient that we can return a data set form and a tabular form of all of them, which is very useful if you're studying, want to study what's there or see what's there to try to pick something out. So we can do one here. Let's take an N-terminal histidine, for example. And this is, we get the molecule object back, and we can show what it looks like. Here, the amino is protonated. This is where the bond was broken. Here's the 3D geometry. We got 3 hydrogens on the amine group, and we can see that the carboxyl is missing the oxygen, as it were, because this would be connected to another amino acid, to the nitrogen, to form the amide bond there. A linking residue, this is histidine in the linking backbone state, and it's been deprotonated at the delta hydrogen. And I can show you what they look like here. Okay, so this one is missing the hydrogen there, and we've got a negative charge on the nitrogen and a negative charge on the carbon. All of these amino acids have the standard labels, and they're labeled using Greek letters starting from the first carbon after the carboxyl group, because that's the way organic chemists typically name the atoms, 100 years ago, back more than 100 years ago, actually. And so we've got C alpha, and then C beta, and then C gamma, and we've got an N delta, that's what the D is, and a C delta, and then a C epsilon and an N epsilon here. And the hydrogens that are attached to them have the same letter. So the hydrogen on the delta nitrogen is HD, and the hydrogen on the carbon delta is HD also. And they have a number appended, and this is what distinguishes this hydrogen from that hydrogen there. And the same for the ones on H beta. We've got H beta 2 and H beta 3. So, and here's another residue here. This is an aspartate, and it's showing its numbering as well. These atom labels are stored in the molecule object. They're stored in the meta information, and the protein editing Packlet functions know that they're there and will use them internally to facilitate the computation. Let's see. Okay. Right now, the user does get to use these labels when they want to conform a residue, one residue to another, because you may have to specify the atom mapping. And we want to be able to use C alpha, C beta, C gamma, et cetera, because it's much easier to do that. Easier for protein chemists to do that than try to remember, is it number 1 or is it number 6 that I need to line up with number 8 or is it number 12? The numbers just don't work well. I'd like to be able to extend the use of this atomic labeling to be able to calculate, for example, the distance between H epsilon 2 and a histidine residue 3 to O delta 2 of aspartic acid residue 34. We need to work out the details for that. We need to work out a reasonable syntax for a user to specify that within the language, and we just haven't done that yet. Okay, to extract a residue, it's pretty easy. We have the function protein residue extract, and you give it a biomolecule and a model number and a chain label and a residue ID. Most experimentally determined structures have just one model. So you can leave the model out, as in this form down here, and it will treat it as though you wanted model 1. So it's a little bit of syntactic sugar for you there. You can also extract several models, several residues, you can extract, several residues, but from a single chain and a residue position from a number of models, or from a single model, you can extract a list of residues from a given chain as well. So there's a lot of flexibility for pulling out pieces to work with them and to study them. So let's get a biomolecule. We'll take the 1 ppt protein, the avian pancreatic peptide, the structures in PDB, and we'll pull it out and we'll get a look at it. And the default visualization is in the ribbon form. I'm using a function here called blue to red to do the coloring. It's at the end of the notebook in an initialization section. So the code is there for you to steal and use on your own. And what it does is it colors the amino acids starting at the amino end, and they're colored blue, and it goes through the rainbow to the C-terminal end, which is red. And it's something that PDB does, and it makes it very easy to see where the chain begins, where it ends, and roughly figure out, judge how far along the chain one is. I've colored residue 16 here black because we're going to do some work there. And the way the color rules work, I can specify a specific chain and residue number and give it a color, and then other rules for all the others residues. And so this is how I achieve this very nice, useful coloring without a whole bunch of code. Okay. So what is residue 16? One way to do it is to use the residue IDs property on the residues property of the biomolecule. If you were at Sutik's presentation a little while ago, he gave a nice overview of working with biomolecules in general at the biomolecule level, and you could have a list of all the properties there, and these are 2 of them. The residue IDs are numbers, but they are not the sequential position in the chain of the data that you have. They are numbered 1 through N for the full residue, for the full sequence of the protein, but the full sequence might not have been fully observed or measured in the experiment. So you might actually have data that begins at residue 6, and it might end at residue, 128 instead of 134, or there could be a gap in the middle. So these numbers are more like street addresses, and so we need to treat them that way. We just can't use them as counting. And so residue 16 was the one we were after, and residue 16 is here, and we can see that it's an aspartic acid. Aspartic acid has also got the single letter code D. So let's pull that out. And whoops. First habit with the navigation keys. Here we are. And here it is. Negative charges on the amide nitrogen and the other amide carbon, and molecule plot will show that this is a carboxyl here by drawing the H. The H really is there. You can see here that in this structure, none of the amino acids had hydrogens on them. So that's one thing we're going to have to fix in the end as well. Okay, so what we want to do is see how it actually fit back on the protein itself. Once we've extracted it, we can use the show function to show the protein as well as the molecule together. And I'm using the space filling plot theme for the residue so that it stands out nicely. And you can see how it looks here on the ribbon model. Now, when we want to substitute that aspartic acid, let's say we want to substitute it with a phenylalanine or F. We can go to the collection of the standard residues and pull out a phenylalanine in a linking backbone state and get a look at it. And we can see that, it's got a phenyl ring out here, and it's a bit bigger than the aspartic acid. The aspartic acid ended right around here, the carbon and 2 oxygens there, and then phenylalanine has an additional 3 carbons that stick out. And the bonds here from C alpha to C beta and C beta to C gamma are rotatable. So, there's conformational flexibility around the side chain of the phenylalanine and also the aspartic acid. And what we want to do is make the phenylalanine look as much like the aspartic acid in terms of the backbone of the side chain torsion angles so that when we put it back into the protein, it fits without a lot of disturbance of the rest of the structure. So that's the conforming process, and it has 2 steps. We first align the backbone atoms, N, Ca, C, and O, the phenylalanine, to the aspartic acid that we've already taken out with the extract. And then what we want to do in a second step is rotate around the rotatable bonds. And internally, we basically make a graph of the 2 molecules. And we can trace out a tree on that graph and then use that to find out what are the rotatable bonds by aligning the 2 graphs to each other. And then we can measure the torsion angle around those bonds, and we can use and minimize to change those torsion angles using molecule modify to set the torsion angles of the phenylalanine until the objective function that's defined, which is the overlap of the atoms or the maximum common substructure, is minimized. That's basically what's going on. And this is all done automatically under the hood. The user doesn't have to worry about it, which is really, really convenient. So those are the 2 steps: align the backbone and then flex the side chain. The protein residue conform function takes the 2 molecules, the representations of the residues. The reference one, in this case, will be aspartic acid, and the residue that we want to conform, the phenylalanine. And you don't need to provide the third argument, which would be the atom mapping. It can figure that out automatically using the maximum common substructure. There are instances where the maximum common substructure might not be as big as you want, and we'll actually see that in a minute. And then you can supply your own atom mapping here using the standard atomic, atom labels, C alpha, C beta, C gamma, etc., to define the mapping. So let's just take the phenylalanine that we took out of the data and the aspartic acid that we took out of the protein, then conform the phenylalanine onto that, basically carriage return time. And here's what they look like overlapped. In green is the aspartic acid, okay, and it goes out to here, and here are the two options is the carboxyl group. And in yellow is the phenylalanine, and you can see that the backbone is well aligned with the side chain up to here, to the ipsocarbon of the phenyl is well aligned. But the phenyl ring itself is twisted relative to the carboxyl group. And gee, maybe we want to let the phenyl ring rotate as well. The maximum common substructure did not map the two carbons, the two orthocarbons of the phenyl ring to the carboxyl oxygens. So we need to do that manually. And so we do it here with this atom mapping. And we're just saying align OD1 of the aspartate to CD1 of the phenylalanine and OD2 to CD2. And we're also including C gamma on both. Automatically, the backbone residues are included for you. So you don't have to go through the trouble of always including the four atoms, the O, the C, the Ca, and the N of the backbone, and C alpha as well. So we can change the alignment by making it a little bit longer. We did it again. And, okay, so let me make sure you do the alignment. Okay, and then to view them, it's like this. And now the phenylalanine is right on top of the carboxyl, which is what we wanted. Now, the next step is to put the phenylalanine back into the biomolecule, and that's what protein residue replace does. Takes your biomolecule, of course, and the chain and the residue ID where you want to insert the residue, and then it's a rule in those two location pieces of information, and on the right-hand side of the rule is the new residue. And it's flexible. You can provide a list of residues to replace at once. If you have several that you want to do, you can do them all at once. And so now we're going to make a new biomolecule by replacing the residue at 16 position, residue 16 by this phenylalanine that we've conformed. And we're going to call that D16F. This notation here is what biologists use to indicate a mutation in a protein sequence. It says that residue 16D was replaced by F. Aspartic acid was replaced by phenylalanine. So I'm just doing it here as well. It's convenient rather than having biomolecule 1 and biomolecule 2 all the time. And then we can see what they look like. And here it is on top of the residue. And this is not the extracted, this is not the phenylalanine from the database. I extracted the 16th residue and then showed it on top of the new biomolecule here. And you can see that it really does fit nicely on there. Okay, now if we go back and look at this, you'll notice that the phenylalanine that we put on has hydrogens on it. The whole rest of the structure is missing hydrogen atoms. So we want to be able to correct that. And that's what the next function does for adding unmodeled hydrogens. The function protein set hydrogens will add any unmodeled hydrogens as well as allow the user to set the appropriate number of hydrogens on the acidic and basic groups for the given pH. So you give it a biomolecule and a pH, and for convenience, if you leave the pH out, it will use a default of 7.4. So here is our molecule that we've modified. Here's the 16th residue here, the new phenylalanine. You can see it's got hydrogens, but none of the others do. And we can add them, and we'll use the default pH of 7.4. Okay, it takes a few seconds to do this. This is, the 0th order version of the code, and I've got to work on getting it running faster. Okay, and then we can see what the result looks like here. Okay, here's our phenylalanine again, and now all the other residues are hydrogenated. And it's at pH 7.4. This happens to be a carboxyl group down here, and you can see that it's missing. It doesn't have a hydrogen on it. And up here is, oh, come on. It's not cooperating. What I'm trying to do is show this side chain here to see what it is. I think it's an arginine. Yep, it's an arginine. And it's got hydrogens on all of the nitrogens because at pH 7.4, it's going to be protonated. This big purple atom here is a zinc atom that is coordinated with a couple of carboxyl groups at the N-terminal end of the amino acid sequence, if you're wondering what that big purple sphere was. Okay. Let's see. Actually, did I jumped ahead a little. Okay. Yep. This is the one protonated. This is the one at pH 1. I wonder how I got ahead. I had mentioned the carboxyl down here. You can see that this does have a hydrogen added to it. And in this one here, you can see that it didn't. So it is sensitive to the pH. And we can also do it at pH 13, very basic, which would remove ionizable hydrogens from the basic groups as well. And it should be ready soon. Yeah, I've got some work to do on optimizing the code. There we go. Okay. And we can get a census on all of the molecules that we've made here. Here's the original biomolecule that we pulled from PDB. And you can see from the count of the atoms here, there are no hydrogens. And then this is the one at pH 7. We've got 285. The pH 1, we've got a few more than that, 291. And at pH 13, we've got 277, fewer than the 285. So this method works very nicely for studying the appropriate number of hydrogens based on the pH, as well as supplying any that were not present in the experimental structure or the folded structure from AlphaFold, for example. Okay, a few odds and ends that I mentioned. Okay, I mentioned that sometimes residues could be missing or individual atoms and things like that. And so I've added a couple of properties to the biomolecule expression so that we can find out about those sorts of things. Up in the previous slide, we saw how we could just use the atomic symbols property to find out if we've got hydrogens present or not. This is the structure of Prambin. from AlphaFold. I downloaded it last night. It's in the zip archive along with my presentation. So as long as it's in the same directory as this notebook, you'll be able to do this import, and we can get a count on it. We can see that there are no hydrogens present. Yeah, we can get a look at that. Both the before and the after. There we go. Here's the before. Here's the after. These two yellow atoms are sulfur atoms from two cysteine residues that form a disulfide bond in carbon that's linking one part of the structure to another part, essentially like a bridge between two different parts of the structure, with different helices of the structure. The other things that we want to look for are non-canonical residues. There are a lot of natural amino acids that are in proteins, but they are not coded for by DNA in humans, for example. They're not one of the 20 amino acids. Bacteria have a number of amino acids that they will incorporate into their proteins that are not one of the 20 canonical ones. They also make amino acids with the D configuration instead of the L configuration. It's C alpha. So those will be different. And then biologists like to put in synthetic amino acids that are not, made naturally, but they want to do that because they want to study the structure. Maybe they're putting something in so that the protein will fluoresce, for example, or it might have a reactive group that when they zap it with ultraviolet light, it causes a reaction to happen at that side chain and change the structure in some way. So they're doing chemical experiments, if you will. So we have non-canonical residues property, which will list all of the residue positions that have a non-canonical residue. Unmodeled residues are ones that were not seen in their entirety. In other words, these were the N-terminal or C-terminal parts that were not observed, or a loop in the middle of the chain that caused a gap. And then there are partially modeled residues. Those are ones where some of the heavy atoms are missing. Some examples here in PDB, the protein 5V63 has some ornithines, sarcosines, and an iodophenylalanine residue in them. And we can see here, we're asking for the non-canonical residues. We see that at positions 1 and 9, we've got ornithines. At position 5 is the iodophenylalanine, and at 13 is sarcosine. I would like to be able to expand our dictionary of amino acids to include things like ornithine and sarcosine, as well as deconfiguration amino acids, just to make it more versatile and useful to biochemists and protein modelers. The protein 4LHF had several residues that were not observed at both the C and N terminal ends of the chain. Residues 1 through 6 were not observed, and 50 through 91 were not observed. And these were the residues that are in the full sequence that were not observed. So we would like to be able to restore them so that you have the full sequence to do the modeling study you wanted to do. And we're experimenting with different methods to try to fold, for example, a hexapeptide, and then glue that into the structure, attaching it to residue 5 to, for example, fill out the N-terminal chain. That's still in the very early stages, mostly planning stages right now. And then the structure 1FNA was missing some atoms entirely from some of the residues. Residue 1 and residue 2, they're at the N-terminal end. The N and C terminal ends are often disordered. In this case, they were able to see the backbone atoms and one or two of the side chain atoms, but not all of them. And so they are partially modeled in KDB parlance. And so we know we need to do some work there to restore the structure to its full complement of atoms if we wanted to do a modeling study. Okay, to correct this problem here, we can most likely just use protein residue replace to replace the arginine and the aspartic acid with the ones from the dictionary, and we should be pretty good to go as a starting point for a modeling study. Okay, that brings us to the end. Thank you for your attention. And I did get finished in plenty of time for questions. And it looks like we have a bunch of them here. Okay, let's see. This is a question from Les. Imagine a future with voice commands like show all alanines in VR, and VR with touch voice commands like delete this alanine and voice minimize structure. Is this less than 5 years away? I can't speculate on the amount of time, but I will say that I have been talking with Charles Poe within the company about VR and AR support, mostly for educational applications. But there's no reason why, a biochemist modeling a protein wouldn't want to be able to do this as well. A lot depends on the hardware you have available to you to be able to do it. Right now, if you have a Macintosh, for example, you can do some virtual reality stuff, augmented reality, I think is what they call it, and put your molecule down on your desktop and, look at it from different angles and stuff, try to turn it around. I've tried it a little bit. This is in Wolfram Language. You can do this, but I find it very distracting to try to look at a model of my molecule with all the rest of the stuff on my desk. So it needs more work. But it's certainly the visualization part is less than 5 years away. The editing commands, depending on how well we can interpret speech and know what to do, we can probably do these things probably less than 5 years. I'm not a betting person, so don't quote me on that. Next question. This one is from Jason. Could the atom naming system, CA, CB, OD2, etc., utilize a display form when labeling in molecule plot 3D, so that they show up as alpha, C, beta, etc.? And Jason is using the Greek letters there in his note. We could probably do that. There is an atom label field that you can put in, but it actually draws it on top of the atom position rather than next to it. And I played with it a little bit, Jason, and I wasn't happy with it. And so I've written this other function that's at the end of my notebook for taking those labels and displaying them. It seems to work pretty well. I forget exactly what option I used in molecule plot to do that. It did the layout very nicely, and all I had to do was tweak the color so that it didn't conflict with the colors for the heteroatoms, the nitrogens and oxygens, and so on. But we can talk more about that next week, about how to facilitate that. But that would be a good thing to do. Back when we were first working on molecule, we tossed around the idea of having atom labels, and that a user could label all the atoms. Steroids, for example, have the standard numbering scheme for each of the 4 rings, and you'd like to be able to use that so that you can refer to parts of the molecule in a consistent way. But it just proved to be not very workable at all because of the sources of structures and things like that. So that never went anywhere. And then another question, this one is from Sergey. How would you go about measuring or calculating the distance between specified atoms in a folded protein? Um, right now, the way I would do that, okay, we don't have a biomolecule value property to measure distances. And at the very least, we should, because close contacts between different helices and things like that is of importance to crystallographers and protein chemists. So we need to be able to support that directly. Right now, what I would do would be to use protein residue extract the two residues, and I would have to get them into the same molecule with the coordinates intact, and then I could use molecule value to get the distance between them. So that last step of merging the two together is, I think, a gap in the technology at the moment. But ideally, you would much prefer to do it in the biomolecule itself. And so we just need to come up with, adding another property to molecule value wouldn't be difficult. But again, it would be, how do we name the atom? We would need to know the model, the chain, the residue, and the atom itself. And we need to come up with a syntax to make that convenient. When I was at Merck in the modeling department and we were first doing proteins and things like that, we had many meetings that ran for hours arguing over what's the right syntax to specify chain, residue, atom, and stuff like that succinctly to make it easy to do exactly this sort of calculation. So, we're going to have those discussions again, but this time at Wolfram. And so we'll tackle that. Probably not this release, but I hope certainly by the next one. I think that's it for the questions. Are there any in the chat window? Here's another one. Okay. Question from Michael. Oh, okay. Can version 15 do delta G minimization or any MD? Okay. Delta G meaning free energy change, gives free energy change. And no, we don't do that. We can calculate an MMFF energy for a biomolecule by converting it to a molecule itself, and that is really just a delta H, if you will. And it's really only a delta H if you're comparing two different conformations. And we don't do any molecular dynamics right now. We've talked about being able to do that. We would very much like to be able to do that, but I think what we would do would be to support an external package like Gromos that does do molecular dynamics, and we would just be able to prepare a straw biomolecule and send it to Gromos, do the molecular dynamics there, and then get the biomolecule back, and then do all of the analysis of the MD trajectory and stuff like that in Wolfram Language. That's what the roadmap looks like right now, but there's no time scale to that roadmap yet. So, but we are talking about that. Another chat question from Jason again, talking about the delta G and electronic structure theory or force fields. And electronic structure on proteins is a stretch, even for density functional theory. But I believe some people are doing it these days. Most of the work on protein energetics is done with force fields. Amber and Charm are the two leading ones. Another chat from Michael. Is there anything in the current version that would support de novo design workflows in general? Actually, yes. I wrote a blog post last January on that, basically redoing what was done by the Baker research group that earned them the Nobel Prize last year on de novo protein design. And it was using the ESN fold service, starting with a protein sequence and folding it, getting it back, comparing it to the target. The target is user defined. In my case, I just wanted to improve the quality of the fold, and then sending that sequence back, perturbing it slightly, changing an amino acid, refolding, and then coming back and measuring its quality, and then optimizing the confidence in the fold, and generating an entirely new protein, never seen before in the world, entirely new sequence that had a very high score for the for the confidence of the fold. And that's basically what Baker's group did. And we can do that now in Wolfram Language. Okay, and then one more remark from Jason about implementing quantum chemistry computations, but for a protein, you really want QMMM. The combination of quantum mechanics and molecular mechanics is what one could do using the quantum mechanics part for the delocalized systems like the aromatic rings and that sort of stuff, for reacting centers. If you were trying to say, let's say, benzene catalysis, you would want to use the quantum mechanical methods for the actual reacting atoms, and then molecular mechanics or empirical force fields for the rest of the protein structure that's, 3 or 4 orders of magnitude larger. But you want to use the simpler method to compute the structure and energetics of that. So thank you, Jason, for the answer to that. And then I will just quickly hop back to Q&A. Let's see. Here's another one from Jason. That would say we did that one already. I should have marked these as answered. I'd like to be able to modify functional groups to reduce the delta G, and increase affinity in Wolfram language. Is there any functional stuff to do that in 15? Using this packlet, you could change the residues. As I said, you could calculate the MMFF energy and use that to guide the changes that you're making. So yes, you could do that with 14.3 in this packlet, in fact. But it would be clunky. It would be slow. Let's see, another question, one from Sergey again. How would you go about measuring, calculating distance? We did that one. And then one from Michael, is there anything in the current version that would support de novo design? And I answered that. So I guess some of you were cross-posting between the chat and the Q&A. That's great. We're just at time now. I think that's it for the questions. So again, thank you very much. As I had said at the beginning, the initialization section here at the end of the notebook on the last slide has the helper functions, the few of them that I use, so they're there for you. Okay, that is it. And thank you again.